This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, all right, it's recording. So this lecture, I would like to start with a brief summary of what you have learned in the previous lecture. And instead of just reading out all this list, I'll just show you some old slides. So we covered conformal transformations in the last lecture. This is just an example of how conformal transformation looks like. So we start with the square in the original plane, which is made up by a group of red lines and blue lines which are perpendicular to each other. And after transforming them through this equation, we can see all these lines are highly distorted, but they still remain perpendicular to each other, and that's the point. So a conformal transformation is a transformation that preserves the angles, which is really important for us in the potential flow. And here is just another example of a non-conformal transformation. This is a simple shearing. We can see the square here is sheared, and in the new plane it goes into a shape like this. And the angle, the 90-degree angle, is not preserved anymore in the transformed plane. So why is the conformal transformation important to us? Let's think about the stream function and the potential function. So if let's think these red lines are constant stream function lines and the blue lines are constant potential function lines, they should always be perpendicular to each other, right, as required by this our definition. So which means that if we define some sort of flow in the original plane and we calculate the stream function potential function, of course we hope that this property should be preserved in the new transformed plane, and conformal transformation will satisfy this requirement. So if a potential function, complex potential function, satisfies the governing equation in the original plane, then after this transformation, it should also satisfy the governing equation in the new plane, and that's the whole point behind what we are doing here. Okay, so these are just some of the examples we are going to need in the following part of the lecture. These are some basic conformal transformations we'll use. This is just a simple rotation. We rotate this group of lines by a degree of theta, and this is the Bartley shift. We can shift this group of lines in the x direction and y direction using this equation. Okay, this should be straightforward. And this is a more complicated example of conformal transformation, but it's very useful for us later on. So this one is the Joukowsky transformation, which is defined by this equation. And the c here is just the radius of the Joukowsky circle. So this transformation is very meaningful for us. Sorry, I should get to the derivative first. Okay, so if we differentiate this, anyway, what I was trying to say is that this transformation allows us to transform a cylinder into an airfoil shape or flat plate in the transform plane, and that helps us with showing some complicated flows that is meaningful to aerodynamics. Okay, so here is the if we differentiate this transformation, we can get something like this, and we'll see that there's a singularity point at z equals to 0. This is okay for us because in the original plane, this point is just the origin, and that's in the center of the cylinder we're looking at. Since we're more worried about the flow around the cylinder rather than the flow inside the cylinder, okay, so it doesn't really bother us that much because we are not looking at the flow inside the cylinder anyway. But Another thing is there are also two critical points where the derivative goes to 0. And we can solve this equation, saying this equation this one equals to 0, and solve it. We get two solutions, which are z equals to plus or minus c. These are just 2 points along the real axis at the positive and negative half of the real axis. These two critical points are very important because the derivative vanishes at those 2 points, which means that if we have a smooth curve passing through this critical point, after transformation, it will form into like a cusp or a kink in the transformed plane. So that's actually this sentence. So this point is corresponding to the sharp trailing edge of the airfoil we're going to look at later. You have covered this in the previous lecture, right? So I'm just going through it very quickly. Please stop me if I'm going too fast or if you have any questions, okay? All right, so here is an example of how the Joukowsky transformation works. This is the original plane, and this red circle here is the Joukowsky circle with a radius of c, and these two points are the critical points. And this blue circle, which is slightly larger than that, is the circle we want to transform to the new plane. So in this case, when these two circles what is called co-centered, the center of these two circles at the same place, and we can show that the transformed in the transformed plane, our cylinder should look like something like this. It's an oval shape. And if we shift this circle in the original plane slightly along the x direction, okay, until the blue circle touches the red circle at this critical point, we can see that in the transformed plane, it formed this teardrop shape or the airfoil shape with the sharp edge at the left half of the plane. And another thing is the ratio between the radius of this blue cylinder and this red circle governs the thickness to chord ratio of the new airfoil, which means that now this airfoil looks really thick, right? But now if I decrease the radius of the blue cylinder, the airfoil is getting thinner and thinner in the transformed plane. And another thing we can do is, what we have done so far is to generate symmetric airfoils. We can also generate cambered airfoil, this kind of asymmetric airfoil, by shifting this blue circle along the y-axis, along the imaginary axis. So we can shift it up while keeping these two circles crossing each other at this critical point. And we can get this cambered airfoil in the transformed plane. Okay? Any questions so far? Okay. Okay, so this part is how do we get the flow in the transformed plane? So we have flow around the cylinder in the original plane. Okay, and we can calculate the streamlines using the either using the analytical equations, or you can use your MATLAB code. You should probably have that fixed by now. Anyway, so you have the streamlines generated in the original plane, and the next step is you want to apply the Joukowsky transformation to transform everything from the original plane to the new plane. And let me take this streamline as an example. You feed the coordinates of this streamline into the Joukowsky transformation. Okay, every single point on this streamline can be written into z coordinate. Okay, and you feed that into this equation, so you can calculate zj, and then you plot that in the new plane, and you'll get a new streamline in the transformed plane, all right? And repeat the same process for all other streamlines. So how to get the streamlines around the circle? We could use our RK4 code written in MATLAB. So this is just an example of how to plot it in MATLAB. The blue lines are the streamlines. And then transforming, just as what I said before, you get Z coordinate using this relation. X is the real axis, and Y is the imaginary axis. I is just the imaginary unit in MATLAB. And then you use the Joukowski transform to transform the Z coordinate into Zj. And then you plot the new coordinate, which looks like this. Okay, and this A is just the radius of the cylinder in the original plane. So what if we consider the size of the cylinder is the same as the size of the Joukowski circle? We'll get a flat plate in the transformed plane. And in this case, the flow isn't very interesting because it's a zero thickness flat plate. It doesn't apply any disturbance to the flow. So this just looks like the uniform incoming flow you have in the initial condition. It doesn't do anything to the flow field. We can rotate the flow around the cylinder by 90 degrees and see how the flow field looks like. So we can apply a rotation transformation to it. Remember what we did a few minutes ago, the rotation transformation. We apply this, and then this is the original flow field after rotation. And in the transformed plane, we can see the flow field looks like this. And then one more thing we want to do is to we want to know the velocity. We want to know the velocity distribution around this object, around the ellipse in the transformed plane. This is meaningful because we want to calculate the lift and drag coefficient in the of the object. So we need to know the velocity, and then we can use something like the Bernoulli's equation to derive the pressure from the velocity distribution. So let's start with calculating the velocity. In the original plane, we can see the complex velocity is defined in this way. We can calculate the complex velocity by differentiating the complex potential function. And in the transformed Zj plane, follows the same rule, but we have to differentiate the complex potential function by the new coordinate Zj. So here we need to use the chain rule, because we know the original flow field, which means we know the original d omega dz, and we know what kind of transformation we are applying. So we know this derivative dz dzj. So in this way, we can work out the complex velocity in the transformed plane through the chain rule. And then, okay, so here's the velocity in the transformed plane. Here's the velocity in the original plane. And this is the derivative, let's call it the multiplying factor, which is related to the transformation we are using. And one more thing, in order to calculate the pressure coefficient, we need the magnitude of velocity, which is just the modulus of the complex velocity, which is calculated this way. And then, so this is the relation of the velocity modulus with the multiplying factor. Okay. Okay. I think from this point is the new slides for this lecture, right? Yeah. Okay. Good. So I'll slow down from here. Okay. So we have calculated previously that the velocity distribution around the cylinder follows this equation. It was a few lectures ago where we studied the flow around the cylinder, if you could still remember that. But anyway, so for this equation, we have V, and then in order to calculate Vj, We just have to find out this multiplying factor. And the multiplying factor, it goes like dz upon dzj. But what we have written before, for example, if you look at this equation, sorry, I'm just trying to show you. Okay, this is not good. Yeah, so, sorry. What I'm trying to say is that the transformation we applied is zj as a function of z. So, let me go all the way back. Okay, sorry. So here we just have to flip it upside down because we have zj as a function of z. So it's easier for us to calculate this one. Okay. Okay, here we go. And then we differentiate this equation. So we got the derivative, which is this. And then we can calculate the modulus of this term. And then we can have Vj in this way. And then how to calculate the pressure coefficient? We have to feed Vj into this relation. Okay, you can see the Vj here, and then substitute that into this equation, so we can have Cp. By the way, how we get to this point is from using Bernoulli's equation, and I think there are some slides later on in this lecture covering that point. But for now, okay, let's have a look at this one. Here is our original cylinder, and these arrows shows the pressure distribution in the original plane, and after transformation, we get an ellipse with the pressure distribution like this. Okay, so we have done everything is good so far, but that was just an example of ellipse. We want to be able to use this for airfoils as well. So there's actually a problem if we take a closer look at this gradient. So when we look at these, so when we want to calculate Vj, it equals to V divided by this term, the gradient. And remember what we said about the critical point. The critical point is the point where the derivative goes to 0, which means that we are dividing V by a 0. That means in the transformed plane, we'll get infinity for Vj, right? So at these 2 points, there's going to be a problem in the transformed plane. But we can't really avoid it because we need the cylinder to touch the Joukowsky circle at a critical point to form that sharp trailing edge. So there isn't really anything I can do about it to avoid this point. So what can I do to stop Vj from going infinite? Any suggestions? No? Okay, so your suggestion is let it be. Surely that's not going to work. Okay, so let's have a look at this example. If we assume the flow is going from right to left, okay, the flow is going this way, and then what will happen is that, let's have a look at this point. Think about the flow around the blue cylinder. We have 2 stagnation points, right? We have one stagnation point here and the other one here, which is right on the critical point. So if we have a stagnation point sitting on top of the critical point, then at this point, the velocity v should be 0, right? So in that case, if I could manage to force the stagnation point to coincide with the critical point, then I can get away from then I don't have to deal with this Vj going to infinite problem anymore. So this is the example of flow around a flat plate with the angle of attack. We start with the flow around the cylinder, okay? And then we want to apply an angle of attack, alpha. Let's call it alpha. So we rotate the incoming flow, and then we perform the Joukowsky transform with C equals to A. So it's transformed into a plane. But if we take a closer look at this transformed plane, we can see that the stagnation point is here, right? It's right where this separatrix touches the flat plate. It's at this point, rather than the sharp edge of the flat plate. Which means that this mismatch is going to cause us trouble. Think about the streamline that goes very close to the flat plate, goes very close to it, and surely it has to bend 180 degree at this point and follow the trajectory like this, right? And that's not very physical. So this is just the problem I was trying to draw attention to, that problem of Vj going to infinity. So to solve this problem, there was a very clever mathematician and scientist living almost a century ago. He gave us a solution to how to fix this problem. By the way, if you find his name very familiar, he's also responsible for the RK4 method that has been torturing in the earlier few weeks of the semester. Anyway, so he proposed a condition, the Kota-Joukowsky condition, which says, well, let me read this out. A body with a sharp trailing edge, which is moving through a fluid, will create about itself a circulation. See, circulation is the key, of sufficient strength to hold the real stagnation point at the trailing edge. For us, this means that we have to adjust the circulation of the cylinder, around the cylinder in the original plane, so we can force the stagnation point to be at the critical point. Okay? This wasn't the issue for us in that example I gave you here. In this example, there's no circulation, and the stagnation point just falls naturally on the critical point. But if we apply an angle of attack to this case, the stagnation point is going to move, and we need a circulation to move it back. Okay, so this is how we are going to adjust the circulation. We start with a small number, and then we can see in the original plane, the flow field looks a bit familiar. Hopefully, it looks like if you still remember the flow around the cylinder with the circulation, the Magnus effect, and you can see the stagnation point has been moved away from its original place. Oops. And then in the transformed plane, the separatrix moves as the circulation increases as well. Let me show you again. So the separatrix at the trailing edge is eventually going to be tangential to this thin edge at this point. Okay. Do you have any questions? Okay, just feel free to stop me if you feel that I'm talking nonsense. I guess probably you're going to ask if this condition, it doesn't seem very physical to me at the first sight. So you're probably going to ask, why is that going to work? Why do we have to force a stagnation point to be at the trailing edge? So here's an example from a flow visualization. This is just a two-dimensional flow around airfoil, and the working fluid is supposed to be water, I think. And these lines, these bright lines you see, I think they are generated by sprinkle some aluminum powder on the water surface, and you can see their trajectory as they flow downstream. So anyway, so this is airfoil at the angle of attack, and we can see that this flow goes very smoothly at the trailing edge, and the stagnation point is right at this point. Okay, so no matter how unrealistic this condition sounds like, we can see that it actually has some, at least it agrees with the experiment. It agrees with our observation, right? So this can be a solution for us to model the flow around the airfoil. Okay, so let's put everything together to have a look at how to simulate a flow around a symmetrical airfoil. We start with the flow field around the cylinder, and we apply angle of attack, which is just to rotate the flow field by the angle of alpha, and then apply the Bartley shift to create the trailing edge of the airfoil, to force the cylinder to touch the Joukowsky circle at the critical point. Okay, these two circles touch at this point, and then we need to adjust the circulation to force the stagnation point to go to the critical point. Okay, and then the last step is to perform the Joukowsky transformation, and now we have the airfoil in the new plane with separatrix with the stagnation point at this tip and the separatrix flowing out of it. It might be a bit tedious for us to go through this trial and error process to adjust the circulation until the stagnation point sits on the critical point, right? So there is actually an easier way for us to solve for the circulation we need to bring the stagnation point to its right place. If you remember this from a few lectures ago, how this where the stagnation points are for a cylinder with the given amount of circulation, you can see that it actually follows this relation. And in order to move the stagnation point to the critical point, which is to move it to the real axis, it has to satisfy this relation with alpha, which is the angle of attack we have been given. Okay, so from this point, we can see theta equals to negative alpha, and we can substitute that into this equation to solve for the circulation gamma, right? Should be straightforward. And this is the expression for the circulation we need for given alpha, for given angle of attack. It's going to be a bit more difficult with the cambered airfoil, but let's have a look at the flow field around the symmetrical airfoil first. This is what we get after performing the Joukowsky transformation, and we get flow field around airfoil with the angle of attack. We can see the flow is coming at a direction, right? The flow is coming at a direction. So we can rotate this. We usually prefer to see the flow coming from right to left, and the airfoil is at this angle of attack. So let's just rotate it. Okay, we rotate it back this by this amount of alpha. And then now the incoming flow is from right to the left, and the airfoil is at this angle. So one more thing I wanted to say is, if we zoom out to see how the flow looks like in a far field, we can see that the streamlines at this point are almost horizontal, right? They're almost straight. which means that when you are sufficiently far away from the airfoil, you could barely feel the disturbance it applies to the flow field. So the flow is just like the uniform flow without any disturbance from the airfoil. Does it make sense? Okay. Okay, so now let's have a look at the equations we need to calculate the pressure around the airfoil. This is nothing but Bernoulli's equation. So in order to get this to work, we need to choose a reference point, P infinity. And in this case, we usually just choose P infinity as the stagnation point. And this one, P4, this everything up with 4 is just the points around the airfoil. Okay, and how to calculate the pressure coefficient is defined as this. And when we substitute the Bernoulli's equation to here, we can get this form that we usually use. So this is telling me that we need to calculate the velocity magnitude around the airfoil. So how do we do that? We have shown previously that V4, which is the velocity in the transformed plane, equals to the velocity magnitude in the original plane times this multiplying factor, dz4. And in this case, we have gone through a few more transformations than what we did before. We did 4 transformations in total: rotation, bodily shift, Joukowsky transformation, and finally to rotate everything back to its original place. So one way to do this is we can keep substituting one equation to another. So see, we want to get a relation between z and z4. Okay, so z4 is a function of z3, and we can get rid of z3 by substituting equation 3 to equation 4. And now z4 is an equation of z2. And to get rid of z2, we need to use equation 2. So it's a very tedious process, right? And you get an extremely long and complicated equation in the end. But you can still differentiate this one and get dz, dz4. Which probably requires a bit of time. And there's another way that you can do this, is the chain rule. So we can break this down into several parts. dz4, dz can be written as a chain like this. We can see that we can actually cancel this dz1 from the numerator and denominator, and dz2, dz3 can all cancel each other out. So it's just a sanity check that our breakdown makes sense. Okay, so now this makes sense to calculate these terms individually. So dz1 upon dz is just to differentiate the first equation, which gives you e to the power of minus I alpha, right? And dz2 upon dz1 is just to differentiate this equation, equation 2, which is just 1. And the same for the other two. So after you calculate all the derivatives of all 4 equations, you put them together, and you get something like this. But I want it to be a function of z rather than z2. So here we have to substitute z2. We have to eliminate z2 again with these 2 equations, and that should be okay now. Yeah. It looks like this. So now I have the this multiplying coefficient, and then I need to calculate the modulus of that, which is just this one, the real part and imaginary part of this term. Okay, so we have this one, and how about the v, the velocity? In the original plane, we need to solve the flow around the cylinder, and don't forget we have a circulation now, so we have to consider these 2 flow fields together. The first term here is just the flow around the cylinder, and now we have to add the contribution from the circulation as well. And then after putting everything together, we have V, we have this dz, dz4. We should be able to calculate V4 in the end. This is just an example of how it looks like in the MATLAB code. I'm plotting all these different terms with regard to x. Okay, it's just like projecting everything on the real plane. So this is I'm plotting the velocity in the original plane now with the circulation, of course, and this is how it looks like. And here is the velocity as a function of x in the transformed plane, x4. And this is the modulus of this multiplying factor. And finally, the velocity v4 we calculated. And here is the pressure coefficient, Cp. Okay, any questions before I move forward? Okay, all right. So this part is, since we have the distribution of pressure coefficient already, let's take one more step to calculate the lift around the airfoil. This is really meaningful, right? This is the whole point why we are trying to design an airfoil. We wanted to generate lift. This is also very important for you, especially if you're working on the lab report of this subject. I think there's a question in the discussion part where you have to compare your measured lift coefficient against the theoretical prediction. So that comes from here. All right, we have the pressure coefficient, and if I integrate Cp around the surface of the airfoil, I can get the lift. Does it make sense? Yeah. We can numerically integrate this in MATLAB using the trapezoidal rule. And for symmetrical airfoils, the lift is almost identical to the lift calculated from the cylinder case. So this is the formula you got in the previous lectures where you were looking at the Magnus effect. You have a cylinder and you have a circulation around it, and this is the lift equation. So if you numerically integrate the pressure around the airfoil, you should get something very close to this. And this gamma is just the circulation, which can be replaced by this expression. Okay, here's the result. This is what we get by numerically integrating the pressure around the airfoil. The blue line is that. And then the red line is that equation we derived from the cylinder case. They're very close to each other. And it's almost linearly proportional to sine alpha to the angle of attack, which means that if you have a higher angle of attack, the airfoil can generate a higher lift. Okay, so the last part of this lecture is we want to show you how to calculate the how to calculate the velocity for cambered airfoil. This is very similar to the symmetrical airfoil, but you just have one more step to do before performing the Joukowsky transformation. So we start with a cylinder. Okay, this is the same. And then for symmetrical airfoils, I just have to shift the blue circle along the x direction until it touches the Joukowsky circle. But for the cambered airfoil, I have to move it upward slightly to generate the camber, right? So I have to shift it upward. And then this time the Butler shift has two components. It has the real component and imaginary component. But I still need to make sure that the blue circle touches the red circle at a critical point. Otherwise, you're going to get some weird weird shape at the trailing edge. It resembles the number 8. You can try it in your MATLAB code. If the blue circle doesn't touch the red circle at this point. Anyway, I'll leave that to you. So how do we ensure the blue circle touches the red circle at this point after applying all this bodily shift? We cannot just go and do this trial and error process. There's actually an equation for that. This is coming from the Pythagoras. Sorry, I can't pronounce that name. Okay, sorry. So if we look at this triangle, okay, this is the center of the blue circle, and this is the critical point. And I'm sketching a line that is perpendicular to the x direction. If I look at this triangle, I should have y naught squared plus c plus x naught squared equals to a squared. Does it make sense? If I look at this triangle. And when we solve that equation, we'll just get expression for x naught. This is the amount of bodily shift along the x direction I need in order for these two circles to meet at this point. Okay, so another thing to mention is that for cambered airfoil, even for zero angle of attack, the stagnation point is no longer located at the sharp trailing edge. You can see that this is the critical point, but when we sketch the flow field of this cylinder, we have a stagnation point here. Can you see the difference? So the stagnation point is no longer at the critical point, which means that it has, even if the airfoil is at the zero angle of attack, it will have a lift naturally generated. So I'm going to call this angle beta. And the beta can be calculated through this relation. Again, we just have to look at this triangle. We have to look at this triangle, and then we can calculate beta from this equation. So what it means to me that we just have to pay more attention when we want to adjust the circulation for cambered airfoil. We start from the original flow around the cylinder, and then this angle theta, which is related to the circulation, is a summation of the angle of attack we applied to the airfoil, and this beta angle that is related to the geometry of the airfoil. Okay, so it's a summation of these two. And then the same story, we rotate the incoming flow by angle alpha, and then apply bodily shift, and then finally perform the Joukowsky transformation to change it to airfoil. And finally, the circulation has to be set by this equation. So we just have an additional angle beta related to the camber of the airfoil. Okay, so that's everything I wanted to cover for this lecture. Do you have any questions? Okay, so if there's no more questions, that's the end of the lecture today. And if you want to take some of these summary sheets, just come here.
calculate uncoupler right? Why did we do that?
That is because theta is the angle related to circulation, right?
Yeah.
We want to have a circulation that is the second point back to the critical point, which is 0 and basically.
Yeah. That's why theta plus the angle of attack.
Or if it's easier for you, you can think about it as theta equals 2 minus alpha, if that's easier for you. Because angle of attack is sitting alpha, and theta circulation is 3 down.
So when alpha is 0, theta is...
When alpha is 0, theta should be 0 as well. That is just like you have an airfoil like this, yeah, and going right onto it. It doesn't matter. For which circulation? Do you mean this? Okay. Sorry, I wasn't very prepared for that. So this data is related to the geometry of the cambered airfoil. If you remember that point from here.
Why we choose this point as the critical point? Why did we use this point?
Because if the stagnation point doesn't fall to the critical point, the velocity will go to infinity in the transport plane. So you have to force the stagnation point to sit on the critical point.
Yeah, but why the critical point is this?
Because they are because the two sectors are touching, right?
Yeah, and if you remember the derivative of Jaworski transform, there are two solutions where the derivative goes to 0, which is z equals to plus or minus c. This is just one solution. Minus c, yes. Does it make sense? Yeah.
What do you mean is here, this stagnation point is?
What do you mean stagnation point is 0?
The velocity, you mean?
Yeah, that's right. Yeah, the velocity and stagnation point is 0.
Thank you. And also for next time, maybe you can raise your volume.
Oh, okay. I'm sorry. I couldn't get that to work. I'm not even sure if you can hear me from the back.
I was sitting in the middle.
Oh, okay. Okay.
So I can hear you.
Now I feel really sorry for those guys who sit in the very last 3 rows.
Yeah.
So
Maybe.
No, I'm just replacing Leon. He's away for this week.
Oh, okay.
Yeah, thank you.
Thank you.
Are there any more are there any more revision sheets?
Oh, sorry. I think it must be gone. Yeah, sorry. Maybe if you have a friend, you can ask him and copy. I don't have the original files, unfortunately. Leon just gave those leftovers to me. I don't have any.
So the part where it's negative would be the top of the...
Yeah, it should be just how the wave is generated.
Okay, so like this region would be the top.
Yes.
depends what I want to do for a niche lecture. I can't do it.